So you had a question about, yep, yep. Yes, yep. So it depends on the question, of course, but yeah, we calculate the derivative, and then we want to find the critical numbers, right? So critical numbers are either going to be where the derivative is not defined, or the derivative is 0, right? So here we can look at that. The one with a fourth. This is problem 102. So you had all right, so you said you calculate the derivative, right? So that's 4, it's x cubed, right? Oh, excuse me. 3 times 2 is 6. Mm-hmm. And then this factors.
Yeah, this is where I got stuck at. Like, I just found the derivative.
Mm-hmm. Fair enough. Let's see here. Right. Let's see here. Since this is homework, you could like try plugging it into, say, if you're stuck, right? You could use, say, Wolfram Alpha or Desmos or something, graph it, look at where the 0 is to this, right? Something like that as a starting point. Once you did that, then that would give you like insight as to how to factor it. But since we're talking about it here, I'll tell you. This is really minus 3 times 2x squared plus 3 times 2 squared x minus 2 cubed. And so you could rewrite this as plus 3 times minus 2. All right. So the point is the coefficients 1, 3, 3, and 1 here. So you can look at that in terms of the and this is x minus 2 quantity cubed. Now, I didn't expect that was necessarily the way you did it, but what I was expecting was you'd like find this polynomial and then like set it equal to 0 using, say, graphing calculator or something, because yeah, once you see that like f prime of 2 is 0, right? You should have been able to see that from like a graphing calculator or something like that, or Desmos, one of these things. Once you see that f prime of 2 is equal to 0, that tells you that x minus 2 factors f prime of x. So then from that approach, then you could have used long division or synthetic division if you prefer to discover how to factor, like this. Minus 4x. So that shows me that like this. So that would have been my first step. And then once you get linear times quadratic, then you should be kind of home free, right? We can factor quadratic always, either using completing the square, or in this case, you probably should just see that that's straight up x minus 2 squared, right? So if if you didn't have this like flash of inspiration, oh, wait a minute, this is by Pascal's triangle, the cube, you know. I'm showing you this because that's like, you know, like a sneaky, interesting way to do it, but the sort of more straightforward way would be to discover this using graphic calculator and then use long division to start the factorization. Okay, once we have all that, that's not the problem. That's the answer to the problem either, right? At this point, we've just done what? We figured out that 2 is a critical number, right? Although, I would point out, once you figure that out, well, let's see what here. Oh, that was it. Find the critical numbers. Yeah. Oh. Okay, I'm sorry. I've forgotten my own problem, but you're right. We are done. Hey, I solved the problem for you. Dang it. I was tricked. Curses. Anyway, this one's kind of interesting. What if you ask the next question, like, what's the intervals of increase, decrease? Where's the concave up, concave down? You know, we could solve that for this problem without too much more work. You guys, can I erase this? Take a picture. So, notice f prime prime of x is really easy to calculate here, isn't it? Once you've found this, you could calculate the second derivative with the chain rule rather than by direct differentiation of that, and you get 3 times x minus 2 squared, right? So let's see here, x minus 2 squared, so there's like a critical number 2 for the derivative, and there's a possible point of inflection for this, but actually it isn't. Let's see here. So if you plug in like 0, you get negative, right? And then you get positive over here for the derivative. And for the second derivative, the only place it's 0 is at 2. It's always concave up, right? So actually 2 here is not a point of inflection. The graph y equals f of x is everywhere concave up, as it happens. And if I had to guess, this you could also write, you could factor this. I'm pretty sure that what that is, I bet you that this, I'm not absolutely sure of this, but it wouldn't be surprising to me if this is 1/4 x minus 2 to the 4th power. Let's see, just to check it for a second. If I, to the 4th power, that's 16. 16 over 4 is 4. That's 4. I bet you if you multiply this out, you get that. So, in fact, this is kind of a silly example, if I'm not wrong. I suspect that this is actually the... So what we're really looking at, the graph of this, it's just here, and it's just, my picture's not quite right. It's more like this. Because the y-intercept is 4, whereas the x-intercept is 2, if I'm right. Now, I didn't ask for all that in that problem, right? But just kind of going ahead a little bit. Do you have another question? So you're stuck on the critical numbers for another one? Or how about number 103? Did that one go better? Here, for 103, let me work something like 103, but not 103 itself. So let me call this 103 tilde. Suppose you had f of x was e to the x squared minus 5x minus 6, plus 6 rather. You're supposed to find the critical numbers of that, right? So we differentiate that. What do you get? right? So since chain rule, very good. So we do what, e to the inside function, right? So why did I just put e to the thing there again? It's because, mhm. Because what?
Like most problems that I've done when we have an e, it just stuff like that.
Right. It's, I mean, to be more, if I think of this as being like e to the u, right? The chain rule says, you know, we have d du of e to the u times the derivative of u again, right? So that is, so this differentiates to 2x minus 5, and then we have times e to the u, which is e to the x squared minus 5x plus 6. Now, we're looking for critical numbers, right? So critical number is where the derivative is either 0 or undefined. This derivative is defined for all reals. That's not an issue. So where is it 0? We need 2x minus 5 equal to 0, right? Because the exponential is never 0, right? So there you go. X equal to 5 halves is the critical number for this one. So the calculation for your problem 103 is very similar. It's just you have to face something like d du of 2 to the power u is what? It's natural log of 2 times 2 to the u, right? I mean, but that problem is very, very similar to this one.
So
When is a number what? A number is not critical for the function if the derivative is non-zero. And it exists, yeah. And I think also generically speaking, like we don't really think about, if you had a function whose domain was like all positive real numbers, I wouldn't really think of minus 3 as a critical number for the function, even though technically the derivative is not defined there. Like I mostly think of critical numbers as points inside the domain of the function where it's not defined, or points that are very near to points inside the domain of the function, like a vertical asymptote for a rational function, something like that. Question? EXP is another notation for exponential. So problem 108, I have f of x equal exp of 9 plus 6x minus x squared, yeah? But you could just as well write that as e to the 9 plus 6x minus x squared.
So it's kind of like logical.
Yep. Oh, yeah. Just here, you're supposed to find critical numbers, and you're also supposed to, find intervals of increase, decrease, and intervals of concavity. So, like, and you're also supposed to sketch the graph, right? So, what's that? Yeah, so we can work it out if you want. I mean, I think it's not a bad use of our time. What's df dx here? Yeah, chain rule again. So let's that's e to the 9 plus 6x minus x squared times the derivative of the inside function. Yeah. That's 0. Yeah. That differentiates to 6, and so we have 6 minus 2x times e to the whatever this is, 9 plus 6x minus x. I think I should have called it u. It would have saved us a bunch of writing, right? But anyway. And so to find critical numbers, right? So f prime of x equals to 0 implies that 6 minus 2x has to be equal to 0 because the exponential is non-zero. So what is x equal to? 6 over 2? 3, right? 3 is the only critical number here. Shadrach, had you,
I just divided 6.
you turned your world upside down. That's what you did. My 10-year-old, for some reason, thinks the word reciprocal is hilarious. Like some days, like my wife will say reciprocal, and he's like, no. It's like, what's wrong with you, Isaac?
Anyway, so
Yeah.
negative 2 cancel.
All right, so then we draw number line, put the 3 here, test some points, like, plug in 2, for example, yeah. What'd you get? 6 minus 4 is 2. 2 times an exponential. Exponential is positive, right? So if this front factor is positive, it's positive, so it's pluses. If you plug in 4, you get 6 minus 8, which is negative. Negative, so it flips. So that shows you that whatever happens at 3, that's a local maximum, right? Exactly, find the second derivative. That's right, we got to count, that's what we got to do, f prime prime of x. So we got to calculate d dx of this function, 6 minus 2x times e to the 9 plus 6x minus x squared. And now it's a product. We have to use the product rule, right? So what goes on here? We got minus 2 times the exponential. I'm going to start using a u because I'm tired of writing that. Plus 6 minus 2x times e to the u times d dx of, well, 9 plus 6x minus x squared. I guess technically I should say let u equal to that, exponent, but I'll write it out in the next step. So this gives us another 6 minus 2x term, right? So we've got minus 2 plus 6 minus 2x times 6 minus 2x, all times that exponential, right? And then we got to multiply that thing out, what we got, Yeah, so 36 minus 2, which is what? 34, right? Do you guys agree? 34 is the constant?
Oh, yeah, my bad, I was still multiplying out.
Yeah, you're fine. And then, so this is, I got a minus 12 and another minus 12, so minus 24. Plus 4x squared, yeah. So you notice that you can factor 4 out of that, right? Can you factor 4 out? All right, so we've got 2 times 2x squared minus 12x plus 17 times e to the u. All right, well, I'm going to start up again here. So we have f prime prime of x is 2 times the exponential, and then this pesky quadratic 2x squared minus 12x plus 17. So this is only going to be equal to 0 when the quadratic is 0, right? So the places where we could have potential inflection points are where that quadratic is 0. To tame the quadratic, I will complete the square. So I factor the 2 out. That's x minus 3 quantity squared minus 9 plus 17 over 2, which is 2 times, so that's 18 halves, right?
Yeah.
So 7, no z's. And so then that's 2 times x minus 3 plus 1 over root 2. Now, I would strongly encourage us to, check our work with, like, Wolfram Alpha or Desmos or something here, because made a few steps, and it's possible I've made a mistake somewhere, but so it's a good idea to check your work, right? But if I haven't made
Just do like the bottoms up. I was taught that way.
bottoms up,
Like you write 2x minus 12x plus 17. But then you take, so when you're gonna rewrite it, you're gonna put x squared minus 12x plus 17, or whatever 17 times 2 is. And then you solve that for the difference of the two squares, but then you go back and divide by 2, whatever you got x minus plus.
you can do it that way if you want, but I don't do that. Like, I'm either going to complete the square, or I could use the quadratic formula. I know there are other sneaky tricks for doing factoring when there's like a 2 out front. I think that they call it slide and divide or something. But anyway, we found it. The critical, so for the second derivative, you should get the same thing. So we're at 3 plus or minus root 2, right? So we're like 1 over here and 1 over there, yeah? Or you could use the quadratic formula to find the zeros too, right? That's another method. But in any event, there's the second derivative sign chart. So, and if we plug in numbers to that, we're going to get positives, negatives, positives again, like that.
So in this video I watched it on YouTube. So this is finding zeros.
No, that the finding the zeros was the first part, the critical numbers,
Okay.
and then that the first part, that's when you found the increase, decrease. The second part is the concave.
That's right. So, but, I mean, I could say this. The critical numbers of the derivative function are the places where we can change from concave up to concave down. So like places where f prime prime of x is 0, those are, technically those are critical numbers for the derivative function. But anyway, we can, now that we have this, we can answer the questions that are asked in that question. Answer the questions which are asked there. Where is it increasing? Where is it decreasing? Increasing minus infinity to 3, decreasing 3 to infinity, right? Concave up. Where's it concave up? Concave up, minus infinity to 3 minus 1 over root 2, and also from 3 plus 1 over root 2 to infinity. Where's it concave down? Concave down between 3 plus or minus 1 over root 2. Yeah. And how many inflection points are there? There's an inflection point at 3 plus or minus 1 over root 2. Those are both inflection points because they're places where you change from concave up to concave down, or from concave down to concave up. Yeah, they're 2 inflection points. And we can sketch the graph, I think. So I'm going to say that's x equals to 3. Oh, let's see, 3, like, that's like 3 plus 1 over root 2. Like that. Excuse me. And let's see here, what's the value of the function at 3?
Can't you say we just plug it into the,
Yeah, so we're graphing the function. Which formula do we want to use? We want to use the function formula, right? So I'm trying to graph the function itself, right? So I should look at, like, what is f of 3? So plug in 3 here, what happens?
So that would be
18. Let's see here. So 9, that gives me minus 9. Oh, man. Woo. You're not wrong. It's just not what I was hoping for. So e to the 18, this is not going to be to scale, right? Like e to the 18. That's pretty big. So I'll draw it here. That's not. E to the 18 is a stupidly large number. But nevertheless, that is a local, what? It's a local maximum, right? And then it's increasing, and then it's decreasing, it's concave, so it's supposedly, concave, changes the concavity here and here, I think. So I think it's something like, it's kind of like concave down like that, right? And then it flips over. I don't know if it turns back up again or not. Let me think about this. What happens to the exponential as x goes to infinity? As x goes to infinity, we get e to a minus very, very large number. E to a minus very large number is 0. And likewise, as x goes to minus infinity, this also goes to e to a minus very large number. So like both directions, as x's go to plus or minus infinity, this is going to 0. So it's basically this. Let's see here. Let me try something out for a second here. This is what? This is actually, I think it's that anyway. E to the minus, we have x squared minus 6x minus 9, right? And what happens there? That's actually e to the minus what? X minus 3 squared? It's not that, though, because that would have a plus 9, right? So it's this minus 18. No, plus 18. Yeah, plus 18. Okay, never mind. This is, what I'm just doing here is not especially interesting. It would have been more interesting if that had been a minus 9 instead of a plus 9, because then you could kind of, well, anyway, I'm going to erase that. It's not helpful. So, other questions? Do you guys understand what it means to verify the mean value theorem for a function over an interval? Okay, let me show you an example of that. So let's say verify mean value theorem for f of x equal to, let's say, x cubed plus 3x squared on the interval from 0 to 2. So, okay, let's calculate what's f of 0. F of 0 is 0. What's f of 2? You got 20? All right. So what's f of 2 minus f of 0 over 2 minus 0 equal to? Yeah, 20 minus 0 over 2, 10. So the mean value theorem says that this average rate of change over 0 to 2 is matched by the instantaneous rate of change at some constant, right? That's what the mean value theorem says. Mean value theorem claims that there exists C in 0 to 2 such that f prime of C is equal to 10. Right? F of B minus f of A over B minus A. Here A is 0, B is 2. All right? So what is f prime of x? Well, 3x squared plus 6x, right? So to verify the mean value theorem, we actually have to find the constant c such that f prime of c is equal to 10. All right? So this gives us the equation, what? 3c squared plus 6c equals to 10. Now, if you don't like working with c, you could use x, whatever. But that's a quadratic equation. We can solve it. All right? I just made up this problem. It's not going to have a nice solution. It's going to have an ugly solution. You know, it's like it's going to be ugly. 3c squared plus 6c. I mean, if this came out to an integer solution, it would just be like just pure luck on my part. I'll use quadratic formula. C is equal to minus 6 plus or minus the square root of b squared, which here is 36, minus 4ac. So that's 4 times 3 times minus 10, divided by 2a, which is 6. So c is minus 1 plus or minus the square root of yeah. Well, the 6 goes over here. That 6 in the denominator has to divide both terms in the sum. Yeah, 156 divided. I mean, I think 4 times 3 is 12. 12 times 10 is 120. Minus minus gives me plus. 120 plus 36 is 156. The square root of 156 is, yeah, that's 4 less than 160. That might be.
I think it's a number. I think it's 14.
I think it's 2 root 39. I think 156 is 4 times 39. So for what it's worth, that's so if you want a pure number, and of course 39 is 3 times 13. So you could do, anyway, there's 2 solutions. Which one of them is the one that will actually be the one you want? I mean, there could be more than one solution in 0 to 2. Are those in 0 to 2? I don't know. I think we need to choose. Yeah, I think we need to choose the which one, the plus one or the minus one. If we choose the minus one, it's negative, right? That's definitely out of. Yeah, so I think we better choose the plus. Yeah. So this number right here, minus 1 plus the square root of 39 over 3. Square root of 39 is a little bit bigger than 6, right? So that's about 2-ish, a little bit bigger than 2. 6 divided by 3 is about 2. 6 divided by 3 is 2, but that's a little bit bigger than 2. So that's definitely between, that's about 1. C is about 1. But there you go, that number, if we plug it into the derivative, it gives us that the derivative is 10, which verifies the mean value theorem. So that's what it means when it says verify Rolle's theorem or verifies mean value theorem. It means to actually, Rolle's theorem and the mean value theorem say that there exists this number that either gives the average rate of change is equal to the instantaneous rate of change, or Rolle's theorem that the derivative is 0. So that's what we mean when we say verify a theorem. It actually, show that it's true for that specific example. Other questions? So I'll give you a hint for problem 114. Oops. Can I erase this one? For problem 114, here's a hint. The fundamental theorem of algebra can be stated as if P of x has degree of P of x equal to n. So here this is a polynomial with real coefficients. Then there exists at most n zeros to P of x, for P of x. Let's say n solutions. Let's say it that way. N solutions of P of x equals to 0. So, problem 114, you've got this function. It's a polynomial of order n. And I think I just told you the answer to part A. I mean, the answer to part A is n. If you have an nth order polynomial, there are at most n distinct zeros. You can't have more. Why can't you have more than n distinct zeros for, let's just talk about that for a second. What if you had f of x is fourth order polynomial, all right? And suppose that you knew that it had 5 distinct zeros, right? Suppose you knew that f of 1 was 0, f of 2 was 0, f of 3 was 0, f of 4 was 0, and f of 5 was 0. Suppose you had 5 distinct zeros. What would be the problem with that? Well, we know the factor theorem, right? The factor theorem says that to each 0 there corresponds a factor. And so f of 1 equal to 0 means that x minus 1 factors f of x. And f of 2 equal to 0 means that there's an x minus 2 factor. And then there would be an x minus 3 factor, and an x minus 4 factor, and an x minus 5 factor for f of x. So what would that mean? That would mean that you could write f of x out with all these factors, which would tell you that f of x is equal to stuff times x minus 1 times x minus 2 times x minus 3 times x minus 4 times x minus 5. And that's not possible because that would mean that the degree of that polynomial was not 4. It's like 5 or more, right? Because when you multiply this out, you got x times x times x times x times x. So for this reason, if you have a nth order polynomial, you cannot have more than n distinct zeros because each zero gives you a factor. And when you multiply those factors out, you'll violate the degree that you're given. So that's the answer to part A. Nth order polynomial, at most n distinct zeros, right? And then like part B, I say what's the maximum number of critical points for the function, right? So then you're looking at the derivative equal to 0, right? But if you look at that, you should be able to answer that in terms of the same idea as we did for part A. I'll just say that. The thing is, the derivative and the second derivative of a polynomial, they're again polynomials. You know? So let me give you a specific instance of the answer for problem 114. Like if we had n equals to 4, right? If you think about it, you have at most 4 zeros for f, right? And if you differentiate a fourth order polynomial, what do you get? You get a third order polynomial, right? So you have at most 3 critical points in this case, right? 3 critical numbers. And what happens when you take the second derivative of a fourth order polynomial? You get two derivatives. You get a quadratic, right? The second derivative of a fourth order is a second order. How many distinct zeros can you have for a quadratic? Well, 2, right? So see, there's at most 2 inflection points for a quartic. At most 2 points. There doesn't have to be any. Actually, we saw 2 inflection points for the fourth order one we looked at in the earlier problem today. We actually saw that happen. The 3 plus or minus 1 over root 2, those were 2 inflection points for a fourth order polynomial. Now, problem 114, the answer is not in terms of, the answer is not 432 for problem 114. The answer has to be in terms of n. The answer to part A is n. All right, so. All right. Mm-hmm. Sure. So Rolle's theorem is harder for me to do because I got to come up with an example that has f of a equal to f of a equals to f of b, right? Because Rolle's theorem says that if f is continuous on the closed interval of a to b and differentiable on the open interval from a to b such that f of a is equal to f of b, then there exists C in the open interval from a to b such that what? The derivative is equal to 0. So really, if you look at it, Rolle's theorem is a special case of the mean value theorem, because that f of b minus f of a over b minus a, that average rate of change is 0 in this instance, Rolle's theorem is a special case of the mean value theorem. Although we used Rolle's theorem to prove the mean value theorem. So they're interconnected. Okay, so I need to come up with an example to verify. So let's see here. I'm going to let f of x equal to, let's say, x squared plus 3x. All right. And I'm going to look at on, let's say, 1 to 2, right? So, oh, I may be asking myself too much here. Oh man, I have to adjust both at the same time here. Let me make it 1 to 3. And x squared minus 4x. That might work. Let me think about that. If I plug in, what's f of 1? Yeah, f of 1 is, I heard negative 3. And f of 3 is what? Hooray! Okay, so this is a contender. Now, fortunately, I didn't ask you to make up a function to verify Rolle's theorem in your homework, right? I said, here's a function, verify it works for Rolle's theorem, you know. I gave you, f of x is given in the problem. Like, the problem of making a function which you can verify Rolle's theorem for is a pain. Mean value theorem's easy, you just make up anything. But anyway, so then what do we have to do? So notice f is continuous. Its derivative exists on 1 to 3, so Rolle's theorem should apply. So we seek C in the open interval from 1 to 3, for which f prime of C is equal to 0. So let's see here, what's f prime of x equal to? 2x minus 4, right? So we need to solve the equation 2c minus 4 equals to 0. So 2, right. Yeah. Then you, yeah, I mean well, I mean, I wouldn't take off points if you did all this. It's clear that you verified Rolle's theorem, but I mean, it would not be bad practice to write a sentence after this that says this verifies Rolle's theorem. I like it.
Is there a lot of difference that when you plug in the numbers, they have to equal each other?
Right. I mean, if you believe the algebra, then it's going to be the case that when we plug in 2, but of course you could say, and so f prime of 2 is 2 times 2 minus 4, which is equal to 4 minus 4, which is equal to 0, which verifies Rolle's theorem, you know. But I would argue that that's kind of superfluous, because if we believe the algebra, we already know that that's going to give us a derivative 0. You know, so I would feel like I'm being a bit of a jerk here if I took off points if you didn't write this last sentence I just wrote. So, all right. Well, I'm gonna move on now. Gotta tell you some new stuff today. The time that remains. So. The next topic in my notes is limits at infinity, all right? And so limits at infinity, the basic thing for limits at, limits at, and I think my title is to infinity and beyond, or something stupid like that. But limits at plus or minus infinity. I think the first thing to know is just your basic function graphs, right? Like, let me just rattle off a few, you know? So what does the graph of e to the x look like? Right? So since we know the graph of e to the x looks like that, we can see that the limit as x goes to minus infinity of e to the x is what? I think I have not moved my camera over here yet, have I? This is maddening. I'm a moron. I'm my own worst cameraman. Let's see here. Ooh. All right, so how about 0, right? Because as x goes to minus infinity, we get very, very close to the y-axis, x-axis rather. On the other hand, the limit as x goes to infinity of e to the x is infinity because it grows without bound, all right? Now, in the notes, I give careful, pedantic definitions of limits at plus or minus infinity in terms of inequalities and such, right? But let me not spend class time on that. Read it, appreciate it for what it is. I'm not going to ask you to prove anything at that level. What I want you to be able to do is to know your basic graphs and be, ready and willing, able to do these kinds of limits. How about this? What if we had limit, if you have something like y equals x to the 2n. So in other words, it's an even, I guess it should go through the origin, right? Even power of x versus, we can have something like that, y equals x to the 2n plus 1, right? Odd power. So here we have limit as x goes to plus or minus infinity of x to the 2n is what? It's infinity both times, right? In contrast, with an odd power, you get going to infinity in the one direction, right? But you get minus infinity in the other. So I can actually write it like that. So it goes to minus infinity as you go to the left. It goes to plus infinity as you go to the right. All right. And let's see here. I think we could sort of more generically say the limit as x goes to infinity of x to the power n, what's it equal to? Think about different cases, right? If n is greater than 0, but n is not equal to, greater than 0, then we get infinity. If n is equal to 0, we get 1, because x to the 0 is 1, right? And on the other hand, if x is negative, you get 0. So for example, the limit as x goes to infinity of like 1 over x, right? And so I would advise thinking about these kinds of limits in terms, there's basically two essential principles that you need. Like 1 over something huge is tiny, right? That's essentially the rule that we use, right? And so if x is going to infinity, if 1 over something huge, it gets super tiny, this is 0. But my point to you is that's also up in this general rigmarole, right? That's one important limit. Another important limit to know is something like this. Limit as n goes to infinity. Well, yeah, fine, n goes to infinity. Fine, x goes to infinity. I'm having trouble with my letters. Of r to the x, where r is a constant. R is a constant, right? So what happens here? Well, if r is positive and larger than 1, what happens? So this would be like e to the x. It would be an example of this, right? goes to infinity. If r is equal to 1, it goes to 1. And it's funny. If r is less than 1, well, if 0 is less than r is less than 1. All right. Then that's is going to 0 right now. The thing is, I wouldn't actually think about something like minus 2 to the x power. This is not a function we think about. This formula is not something we think about in calculus. This is a bad thing. Okay, we actually don't talk about those. Those are bad. Now, great. Now, there are other things which are not quite as clear cut, right? For example, what's the limit as x goes to infinity of, say, inverse tangent of x? See, this one, it helps to take a graphical perspective. So you think about, okay, so tangent is this, right? That's tangent. The inverse tangent is the same shape exchanging y and x. So the vertical asymptotes at plus or minus pi over 2 become horizontal tangents. And the inverse looks like this. So the answer to this, then, is easy to see. The answer is pi over 2, right? Because of this feature of the graph. What's the limit as x goes to minus infinity of inverse tangent of x? Right, we got to look at this part of the graph. As x goes to minus infinity, it's tending to, what is it? Negative pi over 2. Yep. Now, there are other problems. So I have to take a graphical approach for that one. All right. There are other problems where I have to take an algebraic approach, and I think inverse hyperbolic. Well, not inverse hyperbolic, but hyperbolic tangent is a good example. Tangent of x. So what is the hyperbolic tangent? It's sinh over cosh, right? So what is, so sinh over cosh. Sinh is 1/2 e to the x minus e to the minus x. And then you get 1/2 e to the x plus e to the minus x for cosh. The halves cancel, and then look at what you're faced with. Look at what you have to grapple with. E to the x minus e to the minus x over e to the x plus e to the minus x. Right. So what